Welcome everyone to the second TILOS seminar. I just arrived in India today and joining from my parents' home in India. And so excuse me if there is any background noise, because there is always noise over here. So we are very happy to have Professor David Pan here today. So David has an illustrious career, and I was just reading his biography, and I was just wondering what to say. This is like, there is so much in it. I'm just happy to know David and be in touch with him. So he's a professor and Silicon Laboratories Endowed Chair at the Department of Electrical and Computer Engineering at the University of Texas at Austin. David's research interests include bidirectional AI and IC interactions, which are one of the backbones, or maybe one of the foundation of the TILOS Institute. He's an expert on electronic design automation, design for manufacturing, hardware security, and CAD for analog and mixed signal ICs. He has published many papers and is owner of multiple US patents, is member of many editorial boards and conference committees. Notably, he was the general chair of ICCAD 2019 conference and ISPD 2008 conference. He has at least 20 best paper awards from many prominent conferences that I see, including TCAD, DSC, ICCAD, DATE, and so on. He's the winner of SRC Technical Excellence Award, DSC Top 10 Author Award, ASP DSC Frequently Cited Author Award, NSF Career Award, IBM Faculty Award 4 times, and many international CAD contest awards. He has graduated about 40 PhD students and postdocs, and who went on winning many other awards as well. So without much further ado, let's just welcome David. David, the floor is yours. We are grateful to have you in TILOS.
Okay, thanks very much, Ari, for your really kind introduction. So today I will talk about IC for AI, AI for IC and IC for AI, and also closing the virtual cycles. As we know, I think in this audience, we all know AI is really booming, and thanks to the ABC behind algorithms, a lot of data, big data, and the C stands for chips, right? Which actually I work a lot. And the chips not only have CPUs, GPUs, but nowadays there are also a lot of dedicated AI accelerators, right? So, however, when we talk about chips, right, or ICs, right, it's really hard and complicated, as you may know. Nowadays, we are talking about even 5 nanometers, 3 nanometer, manufacturing technology. Anyway, these nanometer scales, and design and manufacturing are extremely complicated. This is a chip that was tapped out a few years ago from NVIDIA. It's called Xavier SoC. It's for autonomous driving. Even at that time, it's using 12 nanometer TSMC process. It has 9 billion transistors. It took 8,000 engineer year to design this SoC. And for such complicated chip, right, usually you have to divide and conquer. For example, you divided them into many of these smaller partitions. For example, 1 to 2 million cells each. But even that, a one backend iteration for timing, power, and all this, right, could take several days. And you probably also heard that Cerebras, which is a very high-flying startup for AI, they are doing an entire wafer scale chip. The entire wafer is a chip. Then you are not talking about billions of transistors. You are talking about trillions of transistors. Anyway, it's unbelievable. And another thing that I like to mention is that what you see at the design, right? Typically, when you design a chip, right, you will ultimately, I'll talk about this shortly, right? You will have high-level designs. Ultimately, you will, write into a mask. Essentially, it's a bunch of rectangulars. You need to manufacture them. However, when you send it to the fabs, because nowadays you are in such small dimensions, like nanometer scale, right? And the lithography still, you are talking about 193, or even EUV, you are talking about 13.5. Anyway, so you will have all this, non-ideal printability, right? So the physics will print like this, right? But that's obviously not good, right? You want to have your chip look like this, right? So then you have to do all kinds of fancy so-called mask synthesis to make it kind of like what you intend. And then imagine, magically, the chip still actually function. It's unbelievable, right? So because of this, the IC design and manufacturing flow, it has been well established, right? There is like a top-down divide and conquer methodology at the higher level, right? The architects and the software people will write system specifications, and then you push down to some kind of NAND gate, NOR gate, those kind of logic synthesis, right? But then you map them to standard cell library, and you need to place them and routing them. This is called a physical design. And then you will do some mask synthesis, as I just showed you, right? And then, if everything works, you will fabricate them and then package and test, right? But even within this, each of these steps, for example, physical design, which I work a lot, right? It has many, many steps. For example, floor planning, placement, and routing, and so on and so forth. And even for mask synthesis, verification, you may need to generate some lithography models and then do all kinds of, OPC and the design rule and so on and so forth, right? And this is not just a linear step, right? So if some of these steps during the fabrication or after fabrication, you found, oops, your chip doesn't work, there's some bugs and so on and so forth, it could be a timing or could be power or could be functionality, right? So you may have to go back to fix it. So that's why the entire iteration is extremely expensive, and you have to better make sure it is first time right, or otherwise there's very expensive, right? So because of this, right, there are tremendous challenges for this nanometer scale design and manufacturing. This is some from performance, power area. In industry, people typically call it the PPA. But the PPA concept, this is just an acronym, but it is extended nowadays to manufacturability, yield, reliability, security, or design cost, or you name, right? So because of this, right, so as you know, right, so the number of transistors definitely grow, right? But on the other hand, the design cost, to design those chips also kind of grow in a Moore's law manner. And that is definitely not good, right? So that's why 3 years ago, DARPA started a ERI initiative, Electronics Resurgence Initiative. And under that, there's an IDEA POSH program. The mission or grant challenge, DARPA to the research community, to academic and industry is that, hey, can we have a no human in the loop, 24-hour turnaround time, kind of new silicon compiler 2.0, right? And among these, they funded a lot of projects, including Professor Andrew Kahn's Open Road, which is very famous, and also other projects. So one of the key motivation behind is, hey, can AI help? And if so, how, right? So certainly AI can help. So that's the main thing of my talk today, right? So on one hand, AI can help to design better ICs in the sense that, hey, can we use all this, modern AI hardware, software, algorithms to enable agile and intelligent IC designs, which can achieve equivalent scaling of Moore's law, right? I mean, many people, if you talk to different people, they're talking, oh, Moore's law is slowing down or dying, right? But hey, Moore's law ultimately is an economics law, and if we can do smarter designs, and that's also equivalent to Moore's law. Meanwhile, right? So as you already know, right? Nowadays, there are a lot of customized ICs and accelerators for all this AI computing need, right? So very interestingly, actually, there's another curve that these two trends for AI and IC kind of correlates. As we all know, right, this Moore's law essentially says, hey, your number of transistors will double every 18 months or 2 years or something like that. That's like exponential for 50 plus years. That's unbelievable, right? But in the last 10 years or so, right, so the number of machine learning archive papers, if you look at this, even beat Moore's law a little bit, right? But anyway, so if you have this exponential kind of, growing, work together, whether it will become exponential, too exponential or whatever, that would be amazing, right? So that's why I think closing these virtuous cycles will be really interesting. So in my talk today, I will show several case studies how we can leverage AI for IC and also IC for AI. I will spend probably 60 to 70% of time on the first topic, and meanwhile I also cover IC for AI a little bit, and so that we can close this virtuous cycle. So for AI for IC, first I'd like to show a case study on DREAMPlace, which stands for Deep Learning Toolkit-enabled GPU acceleration for modern VLSI placement. We are very honored to receive best paper at the DAC 2 years ago. And at this year's DAC, actually I attended last week, we also received the TCAT best paper award. So we also already open sourced the DREAMPlace. It has already been version 3.0 now, right? So what is placement, first of all, right? Placement is a very fundamental VLSI problem, which essentially what is saying that, hey, if you look at this chip, right, and you have this two-dimensional chip image, you have a bunch of these big macros, big macros, right? But meanwhile, you have millions of tens of millions of this dust logic standard cells like NAND gate, NOR gate, inverters, right? But you have to, place them on a two-dimensional kind of chip area without overlapping. And you want to minimize wire length, timing, power, right? Because if you just randomly place them, your performance will be terrible, right? But this is a very well-known NP hard problem. And nowadays, you also have to deal with a huge problem size in modern chips, right? As I already mentioned, right? You may have billions of transistors, and even you partition them, right? You may have millions of cells. So the placement definitely plays a central role in IC design closure because it's in the middle of the entire design flow, as I showed you earlier, right? So somewhere in the middle, you have placement, and without placement, you don't know how long your wire is, right? And modern chip, your performance, power, all these are determined by interconnects, right? So since placement problem is such an important problem, even very early on, right? It has been studied for, every year in DAC, ICCAD, you have a number of papers on placement. So early stage, people have used some partitioning or simulated annealing, or then you do multi-level partitioning and so on and so forth, right? But most recently, people have been using analytical techniques, and the replace from UC San Diego, from Professor C.K. Chen and Andrew Kahn's group, have been kind of considered one of state of the art for this kind of representation for this kind of placement formulation. So what is the typical state-of-the-art nonlinear placement algorithm, right? So typically, you want to minimize wire length and minimize the summation of total wire length, all right? Subject to certain density constraint, right? Remember, you want to spread your standard cells or the cells such that they are more or less, spread out so that later on you can easily legalize them, right? So this is, by the way, is a very classical formulation. And later on you say, hey, I not only just care about total wire length, but I care about timing, but no problem, right? You can just put some weight in front of your wire length, for more important wires, you give it higher weights and so on and so forth, right? And because this is a constraint optimization, and we can make it an unconstrained optimization, make it like this lambda is like a Lagrange multiplier, but but you have to tune this, to really get a high quality placement. It takes a tremendous effort and to get a very high quality placement engines, right? So what's your dream placement engine, right? In general, you would like to have the best quality, and also it has to be really fast, right? Because placement is at the core of the entire design flow, and it has to be run many times, right? And also, you would like to have low development effort, right? And also, you need it to be extensible. If you find some new algorithms and new acceleration techniques nowadays, right, with all these GPUs and AI accelerators, right? So you hope that they can, be easily, applicable to your implementations. So as I always tell my students, when you are doing research, you have to dream big, right? So previously, 10 million cells standard cell placement could easily take hours, right? But hey, can we reduce that to minutes, right? So this is like a dream big part. So actually, one of the motivation behind DREAMPlace is actually observation in recent advancement in deep learning hardware and software. In terms of hardware, right, the GPU actually, compared with the CPU in terms of performance and all this, right, has got significant speed up in like all this neural network training, right? And meanwhile, in the software community, right, there are a tremendous open source effort, for example, from TensorFlow, from Google, and then Facebook's PyTorch, among others, right? So what is the DREAMPlace strategy, right? So essentially, we propose a novel analogy by casting the nonlinear placement optimization into a neural network training problem, all right? So then we can greatly leverage deep learning hardware, such as GPU and open source software toolkits, so that we can develop this a new placement engine very quickly. And meanwhile, we can have really fast parallelisms and acceleration while getting state-of-the-art results. So let me show you the analogy between a neural network training and placement, right? As we all know, right, when we train a neural network, right, so you have a data instance, let's say you have a picture, and then you may want to have a label, whether it's a dog or a cat, and so on and so forth, right? And then you build your neural network, and the one thing you need to train is, hey, what is the weight, right? And then go through the forward propagation, you can compute the error function, right? And then you compare it with your label, and then you can do back propagation, and then you can going through back and forth. Ultimately, you train your weight, right? Then this is a trained neural network, and then next time you give me any picture, I can tell you, this is a dog or not, right? Something like that. But this is just a classification, but you can make it more continuous as well, right? And meanwhile, to avoid overfitting, you can also introduce a regularization function such that to avoid overfitting, right? Very interesting, if you look at your placement formulation, right? We want to minimize the total wire length subject to density constraint, or or you want to minimize the highest density, right? So and you can think about, hey, what is your instance? Your instance is your net, right? And your target is we can set the wire length to be 0, because then the error function is indeed the wire length. And then what is your weight? The weight are the XY locations of all those cells, right? So the neural network here is actually very simple. It's just really the netlist connection. And then through forward propagation, you can compute the wire length, and through backward propagation with respect to your XY location, you can then gradually train it. And surprisingly, this is a really a very nice analogy between neural network training and placement. So one thing I like to mention is that actually we don't really need a lot of training data for our placement engine. Essentially, we are really leveraging the hard computational core of neural network training engines, right? So how those solvers and those nonlinear optimizers and the gradient computation and whatever, ReLU, etc., right? So that's why we can greatly leverage those mature and highly optimized deep learning toolkits. So to develop our new placement, DREAMPlace, right? We just need to plug a new placement API. Of course, we do need to have our own customized wire length computation engine and density computation engine. Due to time limit, I won't go into details here. But here is a key idea, right? We can really leverage a tremendous amount of nonlinear optimizers, and also to match the previous state-of-the-art academic placer from Professor Andrew Kahn's group, right? RePlace, right? We actually use the Nesterov's nonlinear optimizer, but hey, we also use the other nonlinear optimizers. So then compare with the previous state-of-the-art academic placer, which runs on multi-core CPU, and we only use the one GPU, but of course it has many threads, and only one CPU to read the design and do some visualization. And so because we try to match the algorithms and all this intermediate, those steps, right? So we can get the same quality of results. However, using our one GPU, this DREAMPlace, compared with 24-core CPU, right? We get a 30-40x speed up. And actually, this is in collaboration. This is some public benchmark from ISPD released by IBM. This is an industry benchmark. The largest one is like 10 million cells from our collaborator, NVIDIA. So we found that the bigger the benchmark is, the more speed up we have. And the RePlace actually cannot even finish 10 million cells, right? And for us, actually, it can be done in a few minutes, right? This is the first version. And later on, we also actually introduced more accelerations for detail placement and legalization. So now everything can be run in under 1 minute, right? So remember at the beginning, right, we want to big, right? We want to get the best quality results really fast, and we want to reduce the low development effort. As I mentioned, right? So because if you want to develop a state-of-the-art academic placer from scratch, right, it easily could take a year, right? But since we have leveraged a lot of this toolkit, so my students took pretty much like a couple of months. And also, we can also, it is very extensible. I'll talk about it soon. So, well, that's like a dreams come true, right? But we can also dream bigger, right? So, essentially, as I mentioned, right, so we can use different kind of solvers like SDG, Atom, which are widely available in the existing machine learning toolkits. And meanwhile, you may have new objectives and constraints such as routability, timing, or fence region constraints, which basically gives you all different kind of constraints for your placeable objects. So we have extended DREAMPlace 2.0, 3.0, and most recently I just heard that there's a 4.0 for my student now, right, to consider timing, right, and other things. And now there's in the machine learning community there's always all kinds of accelerations, right? So such as multi-GPU, distributed computing, or mixed precision training, right? All these things could be leveraged. And last but not least, right? So there are many other CAD problems, for example, macro placement or gate sizing or any problems, right? We could possibly, form how should I say? You can kind of cast them into kind of a DREAMPlace-like manner, right? So actually, we also have collaborated with Google Brain for macro placement and DREAMPlace, and also got a really good result compared with their original Nature paper, which was published early this year, right? So, all right, so this is the DREAMPlace, the first case study. Now let me talk about the MAGICAL, which stands for Machine-Generated Analog IC Layout. This is a project that I'm leading at UT, more on the analog layout aspect as part of the DARPA IDEA program. We have already open sourced it, and you can download the source code here. So as I already mentioned, right, DREAMPlace mostly focusing on digital IC. We're talking about tens of millions of standard cells, right? Analog IC, doesn't have this kind of scale. You may only have hundreds of thousands of transistors, but they're actually really manually designed, right? Even now, and they're very important, right, to interface to outside world. But the problem, of analog IC design is that there are so many constraints and there are different kind of design objectives, and the analog designers think they have the magical, there's a black magic, right? So, but it's really tedious, and as we scale more to more advanced technology, that's even more tedious, right? So, automatic layout definitely plays a very important role. So our MAGICAL mission is to develop a fully automated analog layout systems, leveraging both human and machine intelligence. We have already published a number of papers on this. So let me just show you the overall framework of MAGICAL. Essentially, MAGICAL has a kind of circuit netlist. For example, in SPICE or spectrums, a certain kind of netlist description with DR design rules, right? And the output is a GDS2 layout, which essentially is a layout which is ready to be manufactured by the fab, right? Well, they will do some mask synthesis, but anyway, this is a final, when people are called tap out, right? That's basically what they have. And what MAGICAL will do is that we have a layout constraint generation to automatically generate, for example, the system or this block level symmetrical constraints. So analog circuit is very different from a digital circuit, right? They really like to have very symmetrical structures and so on and so forth. And so we have used a lot of machine learning techniques and pattern matching, as well as some electrical small signal analysis and graph theoretical. I won't show the details, but this is one of the big chunk of MAGICAL to automatically generate layout constraints, automatically identify subcircuits, and so on and so forth. That's why machine learning can help. And meanwhile, we also have a placement engine. Again, inside placement, not everything is AI, right? So we still have this analytical placement engine, but meanwhile, we use the deep learning for different kind of supermodulars, for example, well generation and so on and so forth. In terms of routing, right? Again, right? Not everything is machine learning. So we have used the machine learning to generate some kind of layout routing guidance, but the ultimate final routing is still done by, for example, a star search type of more like classical routing algorithms widely used by industry. And we also have device generation. Anyway, so I won't, because of time limit, right, I won't show the details here, but hopefully you get a feeling how to do analog layout automation. And analog layout usually is also pretty complicated in the sense that you have, a hierarchical kind of design description. For example, this big block, inside that you have smaller blocks. So our Magical can do this kind of block level synthesis, for example, even for these smaller blocks, and inside this you have even smaller blocks, right? And then you have top level. So basically, Magical can do block level synthesis as well as the top level integration, and so all this can be applied, at a different level of hierarchy. And to test our Magical 1.0, we actually took a very challenging design, which is actually a delta sigma modulator, a third order high performance continuous time delta sigma modulator. And it has actually state-of-the-art performance compared with, so basically the original design was published by my colleague, my co-PI of this project. And it's published at the IEEE solid state circuits letter. And so it has actually, as you can see, right, several pretty complicated design, right? 3 integrators, 2 DACs, and 1 comparators, and a bunch of digital logics, and so on and so forth, right? So essentially, we just read the design in a kind of netlist, and then we actually use Magical to directly generate the layout, which actually we verified, did all the simulation, and sent it to TSMC and 40 nanometer, and it actually tapped out, right? So we got a bunch of chips back and did the measurement. And here is some kind of comparison. As you can see, this is our automatic layout, and this is a manual layout. So one thing we have given to the Magical is that not everything is fully automatic, right? If the designers also know the signal flow, right? You could give it some simple high-level signal flow to guide the layout. In this case, indeed, we used that. But most other things are automatically, layout. And compare with now, by the way, yeah, you can also see, right, why analog design is very complicated, right? So there are a lot of, metrics like bandwidth, FFDR, SNDR, and figure of merit, and so on and so forth, right? So so there are a lot of this kind of metrics, and compare with our this is our fully automatic design with the full manual design. This is by a senior PhD student. It took the students several months, right, to do all the layout. And for us, since this is automated, we can do it in minutes. But if you look at the performance, actually, our performance is very comparable and sometimes even better, right, compared with the manual layout. And this design, by the way, if you compare with some other state-of-the-art designs published in JSCC, CICC, it is still very comparable, right? All right, so now let me also move on and talk about a little bit on the third case study to use machine learning and AI for design and technology co-optimization. As I already mentioned before, right, what you design not necessarily is what the fab can be fabricated, right? So then one thing that people may worry about, hey, if you have this kind of design, does it have some hotspot, right? So that means, for example, this is not good, right? It cannot be fabricated, right? So there are already many papers people have been published, using machine learning to do automatic hotspot detection. Actually, my group published one of the first paper in 2009, and there are probably at this time hundreds of papers on using different machine learning and later on deep learning and so on and so forth, right? But the question that I would like to answer in the next few slides is that, hey, can we do even direct inference to get the printed image? Because if you just have a kind of hotspot detection, it's like a binary classification, right? It's yes or no. Oh yeah, this is good or this is not good, right? Stuff like that, right? But you know, can we directly even get the printed image so that, because this kind of printed image will be used later on, you know, for your, you know, you can use it for yield analysis, you can use it for performance, power, all kinds of analysis, right? So in that spirit, actually, I like to kind of show this LithoGAN, and we also have some other work which is also to generate this kind of printed image, right? So LithoGAN, the key idea essentially is to, without actually doing detailed simulation, you can directly get to the printed image, right? So, but as we know, right, lithography simulation is really, really expensive. And this is just shows you some kind of, you know, rough picture, right? Usually during the design, you give it some kind of layout and mask, right? And then you have to go through the error image, the light systems, and then you have an edge and all this resist, right? So ultimately you will generate this kind of printed image, right? So, that's actually, if you want to do this kind of simulation, even very small area, like 2 micron by 2 micron could take a minute. If you have a 2 millimeter by 2 millimeter, you know, a chip, that means 1 million minutes, right? That's definitely, you know, not affordable. So you probably can only do it once, you know, to do the final verification before you send your chip using massively parallel computing farm and so on. But during the design, there's no way you can do that, right? So our goal is to really try to get this kind of printed image, you know, without running those detailed simulations. I'm sure at this time everyone knows GAN, you know, generative adversarial network, and also conditional GAN, right? So it has been really, really successful, probably one of the biggest advancements in AI community, right? So basically, our motivation, our actually litho modeling is inspired by GAN. Essentially, instead of doing very detailed simulation, once you have all this kind of layout, right, and image, plus all this super resolution assist feature, right, you want to get the final printed image of the patterns that you care about, right? So essentially, we can kind of zoom in and get the kind of, you know, like a influence window that lithography will influence for the features that you are interested in, right? And then, without doing very expensive lithography simulations, using this kind of GAN type of image translation, we can directly get the final printed image. All right, so this is our goal. So again, I won't go into details, and we have a lot of these training pairs. Essentially, you have, you know, for training the CGANs, and then this is our CGAN architecture, right? And it has a generator and also discriminator. I mean, it's pretty standard GAN stuff, right? But of course, we need to customize it for our lithography modeling. And the good news is that actually, it turns out that it actually converges pretty nicely. And we compared it with a very rigorous simulations. We found that it can be thousands of times faster with acceptable errors. And when we discuss with our industry partners, and so that actually is very significant. That means, you know, we cannot say that you can use this for the final verification, but at least at early design stage, right? If you want to quickly identify some problems, and during the design, you can use this to LithoGAN to kind of help to bridge the design and the manufacturing gaps. All right. And another thing I like to discuss is like we can also, you know, bridge the design and manufacturing gap for some security, right? Nowadays we know that, you know, the global IC supply chains, and for design, manufacturing, test, and packaging, and all these, right? So they are, you know, all over the place, right? However, there's a problem, right? So because your chip or while you send your design to some places, or your chip, you know, once it is fabricated or being packaged to some other places, there may be some, you know, bad guys who may want to either reverse engineering your designs, or may put some, you know, kind of bugs or some kind of, you know, trojans in your chip, right? So this is actually a really bad kind of situation. There's definitely a cat and mouse problem, right? Arm racing. So one thing I would like to mention related with learning is that you can use a lot of learning techniques, try to do some kind of, you know, reverse, to be the bad guy, I guess. But of course, you can also use some other techniques. For example, you know, during the IC design, right? How to use smarter IC camouflaging and design insertions, right? To make sure your design is really, kind of bulletproof, that people very hard to reverse engineering, or if they put some kind of, Trojans, you can easily detect them, right? So anyway, I won't go into details, but basically, right, this is something that we can do. One simple idea is to introduce kind of camouflaging. Essentially, you can have two of these. When people try to reverse engineering, they don't know which one is real kind of dummy weir or real weir or dummy weir, and so on and so forth. Right? Anyway, so these kind of things can help to make your really your chip more secure. Right? All right. So far, I have talked about mostly on the AI for IC aspect. Let me spend the next 10 to 15 minutes talk about IC for AI, so that we can close the virtuous cycle. As we know, right? So IC has for customer ICs has been it's pretty much now everywhere, right? Or this from Google's TPU to Apple's or the nowadays, right? The major phones will have dedicated the chips for machine learning, right? For AI. So, but those are mostly based on the conventional this transistors or electronics, right? So what I'm going to talk about is actually a photonic AI chips, which is based on optics or photonics, right? That's why I call it a photonic IC, not just your conventional electronic IC. A lot of this work actually have been motivated by actually a seminar paper from MIT, which was published in Nature Photonics in 2017. Which basically the key idea is that you can play with the light, and then you can also integrate those optical device together with the electronics, and then you can get a really energy efficient and high throughput AI acceleration, right? For in particular, as we all know, right, inside all these AI accelerations, the matrix multiplication is one of the core computation component, right? So after they publish these papers, actually there are a lot of startups, from MIT as well as others. Here I just listed a few, right? So from Light Matters, Light Intelligence, and so on and so forth. Try to actually leveraging, light for AI and acceleration. So what is the key idea behind, right? So the key idea behind this is from the original MIT paper. So the key idea is like, hey, let's say remember, one of the key computation is matrix multiplication, right? Or matrix vector multiplication. So how do you do matrix multiplication using light in and light out, right? So essentially you can think about, okay, here I have light comes in, let's say I have 4 light and they have light intensity, right? Which you can consider them as kind of like a vector comes in. And then the middle part is actually a bunch of optical device, MZI device, don't worry about the details, right? And if they are configured, put in certain array very nicely, you can think about this big chunk in the middle is implement some kind of matrix. And then the output is a vector, which is a product of the matrix vector, multiplication. So essentially, as you can see, yeah, you have light in and light out. This, in that sense, is really doing analog computing, right? So, and then you have very fast detection of this light comes out. And then once you configure this portion and basically light in, light out, it doesn't take any energy to do this multiplication, right? Because you are essentially using the physics and optics to do the matrix multiplication for you, all right? Well, all this sounds very cool, right? However, what's the problem? The problem is that this kind of matrix, so optical device, are very bulky. Because for this kind of device, right? So there are areas easily you are talking about hundreds of micron, okay? And the CMOS we are talking about nanometer, right? So I mean, they are trying to scale it maybe to 50 micron or something, but still, you are easily talking about the 1,000 by 1,000 times the area difference, right? So that's not good. So that means you cannot implement very big matrix multiplication units. And also, this kind of device, compared with electronics, is very mature, right? Optical fabs are still, not very mature yet, and there's a lot of like reliability, thermal issues, and so on and so forth, right? So that's why hardware and software co-design is key. So that's why I'll show you. I hope that we can also motivate a lot of AI researchers here to work together with us, right? So, I mean, there are a lot of optical neural network progress. I know this is a super busy slide, but I just wanted to show you, early on, the people are trying all different kind of neural architecture for, from spiking or to quantum or to other kind of architectures. And then there are, people also try to tap out chips and figure out how it works, right? But anyway, so it's a very active research area, and the device is always, people coming up with new physics and trying to do, this kind of computation. But I will mention the three aspects, basically, the efficiency, as I already showed you, right? The area is very big, so we need to be very efficient. And how do you design your neural network to be very efficient and also robust, and also you would like to really have more learnability from your chip, right? So here is a kind of case study on FFT-based optical neural network, which was published in last year's ASP.DAC, which actually got the best paper award. So I won't go into details. Basically, compare with the original MIT paper, which used a certain device called MZI, right? We do not use MZI because they are very airy, bulky. We actually directly try to configure those kind of optical structures using FFT-based architecture. So you have FFT, you have inverse FFT in the optical domain, and we kind of try to reconfigure this kind of connections and directly build something which can actually do so-called circular matrix multiplication. Well, okay, there's no free lunch, right? So MZI is very general to handle any matrix, but our approach can only handle circular matrix. But in the hardcore machine learning community, people have published papers showing that, oh, circular matrix actually oftentimes is good enough. They have very good expressiveness. So anyway, by doing this, we actually compare with the original MIT paper, we can get up to 3.7x area reduction. In terms of latency and energy, right, we can get a factor of 10 times almost, in terms of reduction. Of course, this is a more theoretical simulation result. We actually even tap out the chip, leveraging FFT, this kind of architecture. The chip has come back. It took us more than a year to really test everything because, to set up all this takes tremendous effort. But we are glad to report that we have tested and it's successful. And, it's actually getting really high energy efficiency and the computational throughput, etc. Right? So, compare with the original one, right? We can have this is a real chip measurement, right? That's why it's like 2x footprint, smaller footprint, and 5x lower latency compared with the original MIT paper. And we also, while you are doing all this kind of, optical IC and machine learning, right? So another thing I like to point out is that you can also, do some innovation in terms of the device. One interesting device that we collaborate with Professor Ray Chen at UT Austin is to have this multi-operand ring resonator. Don't worry about the details, but essentially, when your ring comes in, right? So through this ring, resonator, you can either drop the light or or you still have the light, right? That's why you can actually use it as some kind of binary computation, but you can also use it to do some analog computation. And in particular, you can not only have one control, we can even have multiple control. And through the round trip, you can actually do this matrix multiplication and then summation, right? Anyway, through this kind of new device, then through also some hardware and software co-design, we can build those kind of squeeze light architecture, which has much less device, and compare with the original usage, right? We can actually reduce significantly the power and so on and so forth. And not only this, right? So we also have another work which can do training, right? Most of the work previously, when people are talking about optical chips, they are doing inference, okay? But to do training, of course, you have to have kind of, you have to be able to compute some kind of gradient, right? And we actually use the stochastic zeros order optimizers and to do this kind of, to allow you to do the training. One thing I would like to mention for on-chip learning and training is that, when you are doing actually all these chips, right? So your optical chip may have all kinds of thermal variations and so on and so forth, right? So if you just do software training, it won't be accurate. However, when we are doing on-chip training, because everything is based on the real physics there, right? So you are really using the real kind of whatever, the chip measurement that, not even measurement, you are directly using the physics to do it for you, right? So that's why, if you are doing this kind of on-chip training, you want to have, a reduction in terms of, when you have a software training, but then reduce, map it to hardware, you will actually have like 6 or 7 points of accuracy drop. But if you are doing on chip, you won't have that kind of drop, right? So that's why it's really nice. And we also have done 2 other additional work. This was published in this year's AAAI and also NeurIPS, right? So I won't go into details, but basically, right, while previously when you are trying to train, right, so you may train all the device, right? But that actually takes too much power. But one thing is that you can do pre-training and fix the weight of those devices. You only train a subset of the device. By doing this, essentially, that's why we call it mixed train. You actually can significantly reduce the power and like by 95%, because you only train, for example, 5% of the device, and you can still get a good performance. And another work that we just did is with NeurIPS. We just published the NeurIPS last week. Is not only do gradient-free method, but we can use the first-order gradient. And by doing that, actually, the scalability is much better, and you can train even millions of parameters. Because one of the key ideas is that you are going to use the device and let the light comes in from either this side and the other side, and forward and backward, and then you can really do in situ first-order gradient. Again, I won't go into details, but by doing this, we can actually do a lot of, even much more scalable compared with our original DAC paper, and also save energy. Right? All right, so now let me try to conclude. Right, to recap, in this talk, I mostly focused on some AI for IC aspect. I showed the DREAMPlace, which can do be significant faster, and some litho and LithoGAN. And also the magical to do no human in the loop, and also AI can play a very important role for the security and so on and so forth, right? And in terms of IC for II, I showed the ultra fast, light speed, and energy efficient optical neural network accelerators. As I mentioned, right, the software and hardware co-design is the key. And so I showed. I mean, I didn't have time to show all these details, but basically, right, there's really a lot of room for the IC folks and AI folks to collaborate. So, all right. So I like to conclude in the sense that certainly advance in AI algorithms, software, and hardware can help tremendously how to develop a better IC designs and the hardware. And meanwhile, right, so they can also help to enhance all the AI capabilities, right? So closing those kind of virtual cycle is really, really, I think, as I showed you before, right? Whether it's exponential to exponential, exponential double, but that's times exponential, which of course still exponential. I think there's but still steeper exponential, right? Anyway, so I think that holds a lot of potential. So I like to acknowledge all my supporters and students and collaborators. Right? So thanks very much. I hope we can have some time for some question and answers. Thank you.
Thank you, David.
Yeah, thanks.
It was a very nice overview of how AI is influencing IC design. I think there are a couple of questions in the chat, but I would first ask from the audience if there is any question you want to directly ask David right from the.
I have a quick question.
Sure.
Yeah, David, thanks for the talk. It's very interesting. So for the DREAMPlace, I mean, since you're using neural network itself as an optimizer, there's no real training data in the sense that you don't really need good placement to get started. You just need the loss function. Is that right?
Yeah, we don't need any. Yeah, we don't. Okay, so yeah, very good question, Yusuf. Right, so there are some works which people have used. Some, you may need to have hundreds of thousands of or more, initial placement, and then you train them, then you can kind of do, the DREAMPlace is not using that, right? We also have done some work in that. The DREAMPlace essentially, essentially think about it, it's a nonlinear optimization problem, right? And in your hardcore of your, all the optimizers, right, for machine learning, right, you do rely on those machine learning kernels, right? So essentially, we're leveraging those kernels, right, and to help us, right?
I see, makes sense.
Yeah.
Thanks.
But we cast it into this kind of analogy, right? And the neural network model is very simple. You don't need people may ask, how many layers of deep neural network? And so it's actually pretty simple neural network, right? We just need to use this neural network to compute our wire length, right? And then the weight is our XY location, right? So, and we set it this way, right?
Thanks.
Yeah. So that's why I think if you have any other problem, you can cast it into this.
David, I had a question.
Sorry. Yeah. Sorry, Ari?
Sorry, yeah, I think there is some crossover. There is a delay.
Yeah.
No, I was just asking, I had a question regarding the optical neural network processor. You said that it's basically harder to do matrix vector multiplication. So is there like any error correction issues? Because it seems like you can use some coding theory or like some fault tolerance type of thing there.
Oh, this is a good question. This one is analog computing, right? Essentially, right, your light comes in, goes through here. Maybe let me show it in a more. Can you still see my mouse? Okay, maybe there's a little bit delay. Right, so essentially, right, it's an analog computing, right? So you have light intensity, so light comes in, right? And because of it carries certain information, right? And then you go through this network and then you will have certain light intensity comes out, right? So yeah, this is analog computing, right? So of course, when you're dealing with analog computing, it's not 0 and 1, right? So there's always a little bit of error, I guess, but if it is not very big, so I guess
I see.
okay. Yeah, it's analog. Okay. It's not digital, right?
Okay. So those are sort of self-correcting, and you do not need to do any error correcting codes over there.
Very good point. Yeah. Okay. You have a really great point, right? Of course, your device may have some non-ideal situations, right? So. And because of this, right, your output may have some error. We actually have worked. I didn't have time to show it, right? If you see our some summary slides that I showed here, right, we do have some work on robustness, right? That's actually a really important topic, right?
I see.
If you have some errors, right, or you have some variations, not really error, but let's say you have some variations in your device, right? So how you can train your neural network such that it still works when you are under this kind of variations, right? Yeah, this is a really very important issue. Right? Great question. Yeah.
So there were actually one other question on the chat, but unfortunately, like my connection was going in and somehow I lost the chat. If
okay, I can read that. Okay.
Yeah, so there is one.
The first one is a comment, I guess, or Misha, you can kind of speak. This proves that most papers are written by computers.
That was the joke.
Second one, Muddy, looks great. I'm curious how you specify design constraints for a new design.
Yeah, so that's regarding the magical tool.
Okay, very good. So the constraints. If users know exactly what kind of constraints they would like to have, for example, signal flow in the higher level, or you say, hey, I would like to have some common centroid, or this block and that guy should be symmetric on this axis. Sure, go ahead, tell us.
So I guess the question, how do you specify that, right? Like if you
in a plain text, it's a text. We have a constraint format, right? It's a kind of
got it. Okay.
Magical can read it as a plain text.
And then if you do like a design in GF12 and you move back to Skywater, is those constraints gonna remain the same, or is it like the design need to make a choice or decisions?
Sorry, can you repeat your? I didn't.
I was just wondering if it is up to the designer to make those choices, or you know, it is kind of understood that a sigma delta requires a common centroid, or you know.
Yeah, it is a designer constraint. I mean, Skywater, those are the more DRC rules, right? So of course we need to support different PDKs, process design kits, right, from different you know, fabs, right? But that's of course a separate issue. Another thing that is that we were, or if designers don't give us any constraint, you know, we're trying our best to figure out, hey, you know, based on signal flow, this and that, and or some graph theoretical analysis, or some, you know,
I understand.
We'll figure out the constraints.
So just sorry, I don't want to take too much of your time, but like how much time does it require to port from this PDK to another?
Oh, that takes some effort, right? Because different companies, I mean, even for Cadence Synopsys, those commercial tools, you know, when you put from one process technology to the next, it takes some effort.
Understood.
But I guess, you know, our tool is trying to make very generic, right? So hopefully it shouldn't take too long, but it takes some effort. Right?
Thanks so much.
Yeah, thanks.
There is one more question in the chat from Indira Iyer. Has unsupervised learning been tried for DREAMPlace based on visually good placements, reducing congestions, for example?
This is a really good question. No, in DREAMPlace we haven't, right? Because this is still a very more hardcore kind of placement. But you know, Professor Andrew Kahn's group and my group, we all have done a lot of work to try to predict the congestion using really, you know, data-driven machine learning. We do have some test cases. We figure out, oh, those are more likely to be congested. So you do have training data. But unsupervised learning, that's of course kind of supervised learning, right? Thanks. Unsupervised learning, I'm not sure we have seen a lot, but I guess you can, based on, you know, some kind of pin density, some of this, or connectivity, stuff like that, right? But yeah, that's a great question, right? We haven't seen a lot, but for using machine learning to do congestion prediction, stuff like that, definitely people have done that. Right?
Thanks, David.
Yeah.
I have one more quick follow-up question on that.
Sure.
In the current linear, you know, equation-based, violent density-based optimization that's being done for DREAMPlace, is there a way to seed the weights based on critical nets on the design, or that is just you know, done in a combined optimization, you know, as you explained?
Oh, I see. This is a really good question. So you are saying that typically, I mean, based on my knowledge, right? Typically, when people are trying to do timing-driven placement, right? So they will set higher net weights for more timing critical ones. I mean, you have to do this iteration. That's why, you know, placement runtime is very, very important. It will be run many, many times, right? So you will do some initial placement, you figure out, aha, those are the long wires and those are critical nets. Then you set higher weights, then you redo it. Then you find, oops, there are some other ones which becomes more critical. Then you give that higher weights. But then, you know, it's like non-trivial, right? Of course, the better way is to have a really kind of constraint optimization, but that's super expensive, and people are not really doing it for millions of nets. In smaller, I think IP blocks, right? People may do a kind of linear programming or some kind of mathematical formulation to say, hey, you know, this is a timing critical net. I want it to, you can write it exactly to be less than the clock cycle and stuff like that, right? But that's very, very expensive, right?
Thank you.
Not for millions of cells or tens of millions, right?
Thank you.
Okay. Oh, Andrew has some comments. Andrew, do you want to? Oh, you have to drop off?
Yes, I'm really sorry, but thank you. And I just wanted to say thanks to the seminar committee for twisting your arm, and you're giving this talk, and looking forward to many more in the new year. Bye-bye. Please,
Oh.
please keep going.
Okay, sorry. But Andrew is
Bye-bye.
definitely an expert in all this placement and linear placement. So, but
Well,
anyway.
I think everyone knows where to find you or to find me or our
Sure,
students.
right.
So it's all good.
Okay, thanks.
Bye.
Yeah, are you still there? Indira? I hope that.
Yes, yes.
Yeah.
Yes, can I have a just quick follow-up on that, on the same topic? I don't want to take too much time.
Sure, go ahead.
Okay. Is there a way to set the hyperparameters to basically do a proper seeding of the machine learning algorithm, forward propagation, in the interest of runtime reduction?
Okay, this is a good question. Of course, you have to train it, and there's, I mean, ultimately, once you train it, right, then the placement engine. Oh, are you talking about DREAMPlace or are you talking about general?
DREAMPlace, yeah.
Oh, DREAMPlace actually, so in terms of hardcore engine, we are using leverage that engine to solve it, right? But then, of course, right, how do you tune all this, Lagrangian multiplier and all those things, right? That's a lot of engineering efforts, as so. Okay. Unfortunately, right? So you have to figure out. I mean, there are a lot of different benchmarks. You probably have to try them and so see what is the best convergence and the quality of results. Right? So it takes efforts. Right? And ultimately, of course, you also model it as some kind of electrical static system and stuff like that. I mean, placement is such a fundamental problem, and we really even don't know where the optimal is, right? So maybe there's some new ways to formulate it. And wow, all of a sudden you could improve quality of results by another 10% or something. That would be revolutionary, right?
Right. Thank you so much. Really appreciate your time.
Thank you. Okay.
I think this is one talk where people have many questions, but so I think we are slightly over time. So I will let David go, and thank you very much for this very enlightening talk. We are looking forward to collaborate with you, David, in the TILOS project, and everyone.
Look forward to that.
Yeah, everyone in the meeting, you know where to find David. Email him if you have more questions. Thank you very much. The next TILOS seminar would be in the new year. So TILOS seminar is 3rd Wednesday of every month. So the next one is going to be January 19th, and we will have Shirin Saidi of UPenn presenting from a network perspective in the TILOS project. So looking forward to that. Thanks everyone for coming. Thanks again, David. And we will see you in the new year. Happy holidays.
Okay, thanks everyone.
Thank you, David.
Thank you for attending.
Bye, everyone.
Yeah, bye.
Bye, everyone.